Hi everyone. In this video I will be demonstrating multiple linear regression with a multi-categorical independent variable, and in particular we're going to be focusing in on the use of dummy coding in order to prepare our data for a regression analysis. So before I get started, I do want to mention that underneath the video description you will find a link to the SPSS data file that I'll be working from throughout this presentation, so you can download a copy of the data to follow along. You will also find a link to a PowerPoint that is going to contain a lot more detail that I'm going to be covering in this video, so feel free to download that to learn more. So let us begin by considering our data set. The values that you see in this data set are based off of tabled values from Darlington and Hayes text on linear regression. And in particular, this is from table 9.1. So as you can see right here, we have marital status, life satisfaction, income, and gender ID. So our multi-categorical variable that we are going to be working with throughout much of this presentation is the marital status variable that you see right here. So it's a nominal variable. It's coded 1 to indicate a person who is married. Who is married. 2 indicating a person who is divorced. 3 indicates a person who is single, and then 4 indicating a person who is widowed. The life satisfaction and income variables are both quantitative variables, and then you can see gender ID is a binary variable coded 0 to indicate a person who identified as male, 1 to indicate a person identifying as female. So a common misconception when it comes to linear regression is that it can only incorporate continuous independent variables. So that's not an accurate statement at all. In fact, we can incorporate binary predictors in our regression model. So we could actually perform a linear regression with life satisfaction regressed onto gender ID, and that would be perfectly fine. Now, when it comes to marital status, which is our multi-categorical independent variable, what we would need to do is to convert this marital status variable, or recode marital status, into a set of binary independent variables, and then we can include those in our linear regression analysis. So what I'm going to do right now is just start off briefly by regressing life satisfaction onto the gender ID variable and talk a little bit about those results, and then we'll get into recoding this marital status variable into a set of binary variables, and then regressing life satisfaction onto marital status. So we'll start off again with regressing life satisfaction onto gender ID. So we're going to go to Analyze, go down to Regression, Linear, and we're going to move our life satisfaction variable to the dependent box, gender ID variable to the independent variable box right here, and click on OK. And so now we get our output. So just briefly as we go through this, you can see there's our R-square value indicating the proportion of variation in life satisfaction accounted for by the gender ID predictor. You can see that we have our ANOVA results. The F-test is essentially a test of the testing the significance of R-square, where the null is that the population R-square is equal to 0. The alternative is that the population R-square is greater than 0. So you can see that we have statistical significance at the conventional 0.05 level. So we would infer then that the population R-square is greater than 0. When we move down to the coefficients table, you can see that, again, we only have our single independent variable, which is gender ID right here. So we've got our columns for the regression slope, standard error, there's our t-values and our p-values that are given. So the intercept, which is 77 that you see right here, that is going to be equal to the conditional mean on life satisfaction for males. So you have to keep in mind that when it comes to the intercept is the fitted or predicted value or conditional mean on y when all predictors are equal to 0. So because persons identifying as male were coded 0, then this would have to be the conditional mean for males. The regression slope below for gender ID is 7.444, and that represents the difference in means between those identifying as male and those identifying as female. And in fact, if we were to sum the 77 and 7.444, that would actually get us the mean for persons identifying as female. So you can see that the regression slope is tested for statistical significance, and that test is essentially is a test of the difference in means between those two groups. And you can see we have our t-value that's given and our p-value, and because this is a simple linear regression, the p-value that you see right up here in the ANOVA table is going to be reflected down here with respect to our test of the regression slope. Now you may be asking yourself, why didn't we just test this out using an independent samples t-test? And we can test the difference using the independent samples t-test, but basically the results will be exactly the same. So just to show you what I'm talking about, I'll go back into SPSS, the main area right here, and go under Analyze, go down to Compare Means, and we'll click on Independent Samples t-test. Let me reset that. We'll move marital status to the test variables box and gender ID to the grouping variable box. We'll click on Define Groups and use the correct codes that we have in our data set for those two groups and click on OK. And so you'll see, just for comparative purposes, here's our table of regression coefficients, and then here's the results for the independent samples t-test. So as I said before, the regression slope that's given right here, the 7.444, that is the difference in means between persons identifying as male and persons identifying as female. And then I also mentioned that the intercept is equal to the mean for males. So if we look at the group statistics really quickly from the independent samples t-test output, you can see the mean for males that's given right here, which is the 77. And then if we add or sum these two values, the intercept and the slope, that gets us the mean for females. So you can see also in the independent samples t-test results, there's the mean difference that's given. And when you're performing the independent samples t-test, basically you're taking the mean for the first group and subtracting the mean for the second group, then dividing that by its standard error. So that's the reason why this value right here, the mean difference, is negative instead of positive that we see up here in our regression table. Yeah, and you will also see too that here's our p-value for our results testing the regression slope, and the two-sided p for the independent samples t-test. They're exactly the same. So you can see that we effectively were able to test the difference in means using linear regression. Now this is an important concept to keep in mind, because when we are utilizing something like dummy coding in order to model the effects of a multi-categorical variable on the dependent variable, what we're going to be doing is analogous to performing analysis of variance. So now let's go back to our data set right here and revisit our marital status variable. Once again, the ones indicate persons identifying as married, 2 is for divorced, 3 is for single, and 4 is for widowed. So as I mentioned before, what we're going to need to do is to recode that original marital status variable into a set of dummy variables, and or it's also referred to as indicator variables. So the number of dummy or indicator variables is equal to the number of groups, we'll just call it J, minus 1. So because we have 4 groups for the marital status variable, then that means that we're going to have 3 dummy variables that we are going to be generating for inclusion in our regression analysis. And basically when we are performing dummy coding, what we're going to do is to use a system of zeros and ones to represent group membership. So you'll see that for D1 right here, I've coded married 1 and all other categories 0. For D2, I've coded the divorce group 1 and then all remaining categories 0 as well. Then for D3, you can see that I've coded 3 for group 3, which is single 1, and then the remaining categories are all 0. Now this is just one approach to dummy coding this set of categories. But in this particular system, you'll notice that married is represented by a value of 1 on D1 and 0 on D2 and 0 on D3. The divorce category is reflected in codes of 0, 1, and 0. For single, we have categories of 0, 0, and 1. And then you'll see that the widowed category, that coding is 0, 0, and 0. So in other words, with 3 dummy variables, we have effectively represented all 4 categories. And so with that, then we can use these dummy variables in our regression model. So you might be asking yourself, why don't we have a D4 with codes of 0, 0, 0, 1, where the widowed group reflected. And the fact of the matter is that this particular variable right here would contain redundant information with the previous 3 dummy coded variables. So then you end up with a problem of singularity when you run your linear regression. So we don't want to include a dummy variable right there. So you'll notice though with 4, again, we have our codes of 0, 0, 0 across our 3 dummy variables, and what this represents is the fact that I'm treating the widowed group as a reference or baseline category. So in other words, when we run our linear regression, the first regression slope for D1 will represent the difference between persons who are who are married and those who are widowed. The slope for B2 is going to represent the difference in means between persons who are divorced and widowed. And then the third slope associated with D3 is going to represent the comparison of means between the single group and the widowed group. So there are several different ways in which we can perform our dummy coding in SPSS. So I'm going to give you a couple of ways. First off, one conventional way is just to go to transform, go to recode into different variables right here, this little drop down menu. We can move marital status over to the this box right here, and then our output variable, I'm going to create my first dummy variable. So I'll just call it D1. Press change, and then we'll go to old and new values, and then where it says old value, I'm going to type 1 to indicate a person who is married, and we're going to convert that value. We're going to leave that value set at 1, so we don't really need to change anything there. So we'll click add, and then for group 2, we're going to the old value will be 2, and then the new value will be 0. Add. Then for the single group, group 3, it'll be 3 and 0 here. Click add. And then for the fourth group, we'll type 4 and 0 and then add that as well. So we'll click on continue and then on OK, and now you'll see that we have our new variable that's been generated. That's the D1. So we need to do that 2 more times, so we'll go back to recode, and in this case I can just highlight this, and now I'm going to create a new variable, so I'll just type in D2 and change, then go to old and new values right here. So that first group, the married group, I don't want them represented on the dummy variable with 1. I actually want to change this to 0. So we'll click change. The second group we want represented with a 1, the divorce group. So we'll change 2 to equal 1 right there. So we'll make that change. And then the remaining codes are going to be exactly the same. So we'll click on continue and then OK there. And then finally we'll do the last one, so we'll do recode into different variables. So I'm going to click back on this and create a new variable called D3. We'll press change, old and new values. And then in this case we're going to change the 2 to a 0, since now we're going to be working with the single group, so we don't want the divorce group to have a code of 1. So we'll press change and then we'll go to 3 and convert that to a 1 right there, and then change that, and so now we have all of our dummy variables. So I'll go through here and click on OK there. So now we have our 3 dummy variables. So we'll run our regression analysis by going to Analyze, Regression, and Linear. I'm going to reset this and move life satisfaction to the dependent variable box and D1, D2, and D3 to our box right here and click on OK. So now as we're looking at this, our output, you can see that the R-squared value is 0.421. So what this means in this context with our three dummy variables is that as a set they account for about 42.1% of the variation. Or you could think about it in terms of that our compound variable, which is marital status, is accounting for 42.1% of the variation. And so Darlington and Hayes, in their book, they refer to the set of variables as a compound variable. So they contain all of the information concerning group membership on the original variable in the set of those binary variables, or our dummy variables. So at any rate, the F value that's given right here, or this F test that's given, this is essentially our equivalent to our one-way analysis of variance. So you can see right here that we have statistical significance at the conventional 0.05 level, and that's just basically indicating that we have significant differences among our groups with respect to life satisfaction. If we scroll down a little bit further, then we have our regression coefficients that are given. And recall what I said before about the intercept, or the constant in our model. That is the conditional mean on the dependent variable when all of the predictors are equal to 0. So in our regression model, recall that there's only one group that has zeros on all of our dummy variables, and that is our reference category, which is the widowed group. So what this intercept value is, the 71.5, that's indicating the mean on life satisfaction for persons who were widowed. Then we have D1, and the regression slope for that particular predictor right there is going to represent the difference between the variable that the group that's coded 1, in this case it's going to be the married group, and the widowed group. So in other words, this represents a comparison of two means, basically the mean of the married and widowed groups. And in fact, if we were to sum those two values right there, that would get us the mean for the married group. So you can see that the married group, basically individuals in that group scored on average about 14 points higher with respect to life satisfaction than individuals who are widowed. And the difference in means between those two groups is statistically significant. Then with D2 right here, recall that for that particular variable, that is we've coded that variable 1 for divorced and zeros for all the other groups. So the regression slope that you see right here is going to represent a comparison of means between individuals who are divorced and widowed. So you can see with this slope of 7.7, that indicates that individuals who are divorced scored 7.7 points higher on average life satisfaction than individuals in the widowed group. And you can see that that difference, though, is not statistically significant at the conventional 0.05 level. Then for D3, recall that it was the single group that was coded 1 and all of the other groups coded 0. So the slope right here is representing a comparison between individuals who are single and individuals who are widowed. So individuals who are single scored about 10.9 points higher on average than individuals who are widowed, and that difference is statistically significant at the conventional 0.05 level. Now, briefly, before I move on to the next example, I had mentioned that the ANOVA that is carried out right here is equivalent to a one-way ANOVA, where we have our marital status variable serving as the independent variable and life satisfaction serving as the dependent variable. So just to kind of demonstrate what I'm talking about, I'm going to go under Analyze and then go down to we'll just use the general linear model route right here. Go to Univariate, and I'll move life satisfaction to the dependent variable box, marital status to the fixed factors box. We'll click on Options. I'll just go ahead and click on Descriptives and Effect Size right there. And then under Estimated Marginal Means, I'll just select both of these and move them over to the Display Means box, and we'll click on OK. And as you're looking at this, just kind of keep in mind what we had seen before. In fact, we'll just kind of take a quick look here. The F value is 3.8 0.885, and the significance level is 0.029. If we scroll down to our ANOVA output, you'll see that for our marital status variable, the F value is 3.885, P value is 0.029. And within this particular context, you'll see that the partial eta squared value is actually equivalent to the r squared value that we had generated above. And you'll see underneath the table that the r squared value, it says 0.421. There's also the adjusted r squared, which is also shown in the regression output above. So you can see that we've performed essentially a one-way ANOVA by way of a regression analysis using dummy coded variables. Now, we don't have to treat the last group with respect to our categorical variable as the reference category. We could treat any group as the reference category. So for instance, let's say that I wanted to treat the married group as the reference category. In that case, I would be coding married 0. I would leave zeros for divorced and single, and then for widowed, instead of using a 1, instead of having this set at 0, I would set this at 1 right here. And so when it comes to interpretation of the regression slopes in this context, the regression slope for the first dummy variable would basically be a comparison of individuals in the widowed category against individuals who are married. Then we've got, for B2, it would be a comparison of individuals in the divorced category versus individuals who are married. And then the slope for B3, or for the D3 variable, it would involve a comparison between individuals who are single and individuals who are married. By the same token, let's say that I wanted to use the divorce category as the reference category. So in that case, I would be using a 0 right here for divorce, so that we would have 0, 0, 0 across our three dummy variables. And then I would need to add a 1 for one of the categories on D2 to represent another comparison. So you can see right now that D1, we have married that's coded 1. On D3 we have single coded 1. So the only group that's left over on D2 would have to be the widowed right there. And so in that case, if I was to set it up this way, the regression slope for B1 would be a comparison between married and divorced. The regression slope would be a comparison of means between widowed and divorced, and then B3 would be representing the comparison between individuals who are single and divorced. So let's go ahead and do another analysis where we recode marital status into a set of binary independent variables, basically dummy coded variables. And in this case, what we'll do is treat the married category as being our reference group. So in this case, though, instead of using the recode options that we had used before where it says recode into different variables, in this case I'm going to use an option that seems to be available in SPSS 28 where it says create dummy variables. So first off, I'm going to get rid of these variables right here, and I'm going to go back to transform and go to create dummy variables. So right here I'm going to move the marital status variable over to the create dummy variables box, and where it says root names, what I'll do is I'm just going to call these, we'll just call it dum for dummy variables. So that's going to be the root name associated with the variables that are created. For the value order, I'm going to leave this set at ascending, and then we'll click on OK. And so now you can see that we've got dum1, dum2, dum3, and dum4. So you can see that with this particular coding right here, you'll see dum1 basically is the married group that's coded 1, everything, all the other categories coded 0. Dum2, we have the divorce group coded 1, and all other groups coded 0. Dum3, we've got the single group coded 1, all other categories 0, and dum4 coded 1, that's our widowed group, and all other categories 0. So to perform our regression analysis where we treat the married category as being the reference group, then of these three dummy variables, I'm going to be using dum2, dum3, and dum4. So basically, using the option that I was showing you, it's going to create all possible dummy variables, and then you need to select the correct subset out of that to perform your analysis, because we don't want to include dum1 because that would create a problem with respect to our regression. So we're going to use dum2, dum3, and dum4. So now what we'll do is we'll go to Analyze, Regression, Linear, and in this case we'll move our marital status variables for dum1, dum2, and dum3 over to our box, and then click on OK. So now you'll see once again our R-square value is exactly the same as before. You can see our F test is exactly the same. So the overall fit of the model is exactly the same as before. But now when it comes to interpretation of the intercept, we would interpret the intercept as being the mean on life satisfaction for our reference category. The reference category of married that's the group that's coded 0 across our dummy variables. So the mean for individuals who are married is 85.5, and then you can see that we have differences in means between each of the remaining groups and the married group. So you can see where it says marital status equals divorce, this is the next dummy variable that's given, and you can see that the regression slope is negative 6.3. So if I was to sum these two values together, that would get me the mean for the divorced group. And you can see that based on the regression slope of negative 6.3, that individuals who are divorced scored 6.3 points lower on average than individuals who are married. And that difference, though, was not statistically significant. When it comes to the single category, we have the slope is negative 3.1, indicating that individuals who are single scored 3.1 points lower on average than individuals who are married. And you can see that that difference, though, was also not statistically significant. But when it comes to widowed, we have a 14-point difference between the two groups. So individuals who are widowed scored 14 points lower on average than individuals who are married, and the difference between those two groups is statistically significant. So you can see right here that this option is a pretty quick option. So if you do actually have this in SPSS, it makes it a lot easier than, or a lot more efficient, I should say, than using the option for recoding into different variables. So let's do one more. In this case, we'll go back. We're going to treat the divorce group as being our reference category. So you'll see that in this case, we would use dum1, dum3, and dum4 because in these particular cases right here, or in this case right here, our dum2 variable, that's the one that codes the divorce group with ones right there. So we don't want to include dum2 in our analysis. So we'll go ahead and rerun our analysis. We'll go to Analyze, Regression, Linear. I'll move these three variables out, and then we'll go with married right here, single, and widowed right there, leaving the divorced dummy variable out. So we'll click on OK and take a look at our output. And so once again, we see there's our R-square value and the F-test that's given. All those are exactly the same as before. So the only thing that's different is that we've reparameterized our model so that, and that changes the meaning of our regression coefficients. Remember that our divorce group is our reference category, and it's coded 0 across those three dummy variables. So the intercept, that's the mean life satisfaction for individuals who are divorced. Then we have a comparison between married and divorced. You can see that the regression slope is 6.3, which is in the opposite direction of what we had seen above. If we kind of go back up here, remember that the married group was our reference category, and so right here with this slope right here, you can see that individuals who are divorced were scoring 6.3 points lower on average than individuals who are married. Down here you can see with our regression slope that individuals who are married are scoring 6.3 points higher on average than individuals who are divorced. And so again, this difference is not significant. When we compare individuals who are single versus divorced, that comparison is indicating no significant difference in means. And then when we compare widowed versus divorced, Individuals who are widowed still scored about 7.7 points lower on average than individuals who are divorced, but that difference is not significant at the conventional 0.05 level. So another thing that I want to show you too is that we can incorporate additional variables in our regression analysis. We just have to interpret the regression slopes a little bit differently by considering them as partial slopes instead of unconditional slopes. And what that basically means is that when we are interpreting the effect of a given variable on the dependent variable, then we interpret the slope as reflecting the effect controlling for the other variables in the model. So what I'm going to do now is add in life satisfaction as a predictor income as a predictor of life satisfaction, along with our previous dummy variables, where again the divorce group is going to be our reference category. So in this case, I'll go to Analyze, Regression, Linear, and we'll add in income as a predictor. So now when I do this, when I click on OK, you'll see the R-square value increases. It's actually now 0.768, and the F test that's given right here is indicating statistical significance. So as a set, our predictors are accounting for about 76.8% of the variation, and we would infer that the population R-square is greater than 0. Now, in this particular case, though, the effect that is being shown with the R-square value is of the entire set of predictors. So if we scroll down and we look at our coefficients table, you can see that yes, we still have those previous dummy variables, but now we've added in another variable, which is income. So the R-square value is reflecting the combined effect of all those variables within our model. And so the F test that's given right here is not actually a test in this case of the effect of our marital status variable, or the of the compound variables. In this case, it is representing a test of the entire set of variables. So if I want to test the combined effect of our binary or our dummy variables on life satisfaction, I can isolate that effect by using a hierarchical multiple regression. So to show you what I'm talking about, I'm going to go to Analyze, go down to Regression, and then I'm going to go down to Linear again. And in this case, we're going to go back. I'm going to reset all this. We're going to move life satisfaction to the dependent variable box, and we're going to move income. We'll keep our married, single, and widowed dummy variables included, and then we're going to press Next, and now we're going to click on Method and click on Remove. So this is going to be this block is going to include variables that we are going to be removing. So what I want to do is I want to remove my my dummy variables. So I'm going to remove the married, the single, and the widowed dummy variables, and then we're going to go to Statistics and click on R-squared change. So when I click on Continue right here and then on OK, now you can see that I have a hierarchical regression kind of working in reverse. So the first model is the model that I'd shown you just previously. There's the R-square value of 0.678. There's a test of the full set of independent variables within that model. Model 2 basically represents the effect of income after removing the effect of marital status. So there's the R-square value that's given right there of 0.571, and you can see that that model is statistically significant. But the thing that's really important are a couple of things that's really important. There's the R-squared change right here. The R-squared change represents the reduction in the R-square by removing those dummy variables reflecting marital status. So you can see that the R-square decreases by almost 20%. Now, the F change that's given right here and the significance level that's given right here, this is an F test reflecting the change in R-square as a result of removing our marital status dummy variables. And you can see that we have statistical significance. And what this is basically going to equate to is if we were to run an ANCOVA with income as the covariate and marital status as the independent variable, then this test result right here is going to equate to the test of the effect of marital status on life satisfaction after controlling for our income variable. And just to show you what I mean by that, I'm going to go back and rerun the analysis using an ANCOVA. So I'm going to go back under General Linear Model and click on Univariate right here, and we're going to move income down to the covariate box. Again, I'm going to kind of do a little bit of resetting on a couple of things right here, move this over, and click on OK. And so now when we look at our ANCOVA results, for the effect of marital status right here, you can see the F value is 4.240, significance level is 0.023. If we go back up, once again, just to take a quick look at the change in R squared, there's the 4.240 for the F change and the p-value of 0.023. It's exactly the same between those two outputs. Okay, so now let's go back to our original regression analysis where we included our life satisfaction along with our dummy variables for married, single, and widowed. So in this particular case right here, let's just take a quick look at our coefficients table. So recall that the intercept is equal to the conditional mean on the dependent variable when all of our independent variables are equal to 0. So this, recall that our reference category was the divorce group. So what this value of 47.807 is indicating is the conditional mean for individuals who are divorced but who also have an income equal to 0, because again the intercept is equal to the conditional mean when all of our predictors are equal to 0. So that would include the idea that income, when it's 0 among the individuals who are divorced, that would be the mean for that particular group. With respect to looking at the regression slopes, these are just, again, the differences in conditional means. But in this particular case, the means are all adjusted for the income variable. So the difference between individuals who are married and divorced is 5.371 right here. You can see that that difference is not statistically significant. The difference between individuals who are single and divorced is 4.7, and that difference is not significant. And then when we compare individuals who are widowed and divorced right here, we see that that difference is not significant. We do see within the model that income is a positive and significant predictor of life satisfaction. Now, one last thing that I want to show you is where I recode the income variable so that 0 does not reflect the absence of income, but rather it reflects the mean income. And then we'll just talk briefly about how that affects interpretation of our intercept. So you need to keep in mind that when it comes to interpretation of the intercept, it only makes sense if if values of 0 are theoretically possible on all of the variables that are included in your regression analysis. If it's not the case that there are values of 0 that fall within the range of possible values, then the intercept can become nonsensical when it comes to interpretation. So one thing that you can do, though, is to mean center predictors in your model in order to make the intercept more interpretable. So for what I'm going to do in this case is I'm going to take my income variable and mean center that variable. So mean centering just basically means that I'm going to take the raw scores on income and subtract the mean for income. That's basically it. So we're going to create a new variable in our data set representing that. So the first thing that we're going to need to do is to go to Analyze Descriptive Statistics, Descriptives, and we're going to move our income variable over to the variable box, click on OK, and you can see that the mean for income is 56.9. So in order to create our mean centered variable, what I'm going to do is go to Transform Compute Variable, and I'll call this income, and then I'll just say .cent for centered. So that's the name of a new variable that I'm creating called income.cent. So then I'm going to type in the name of the, excuse me, it looks like I've just overwritten what I just typed in. So I need to move over to the numeric expression box, and I can either type or I can just move it over income minus 56.9, and we'll click on OK. And so now we have a new variable in our data set that represents the centered income variable. So when we center it, the mean of that centered variable is 0, and you'll notice that we have values that are positive and negative. Positive values are indicating cases that score above the mean on income. Negative values would indicate cases that are falling below the mean on income. So now when we rerun our analysis, go back to regression and linear right here. I'm going to reset everything. I'm going to move life satisfaction over. We'll keep our 3 dummy variables. So we've got our first one for married, then we have single and widowed right here, and then we'll move the income variable over, the centered income variable over, and then click on OK right here. So looking at our output, you can see the R-square value is exactly the same as what I'd shown you before for the previous model. There's our F value for the full model as well. And again, if I wanted to test the effect of the compound variable marital status using our 3 dummy variables, then what I can do is do that hierarchical regression strategy that I just demonstrated a few minutes ago. So in this particular case, looking at our regression coefficients, you can see that the constant, or the intercept, is 78.289. And just to reiterate, the intercept is interpreted as the conditional mean on our dependent variable when all of our predictors or independent variables are equal to 0. Well, when I mean centered the income variable, it rendered 0, or it basically means that 0 is falling at the mean of the income variable. So in this case, I would be interpreting the intercept that's given right here as the conditional, the mean on life satisfaction for divorced individuals who are also falling at the mean on the income variable. You'll notice too that all of the remaining regression coefficients within the model are exactly the same, as well as all of our significance test results. Okay, so that pretty well rounds out my discussion of multiple regression with multi-categorical independent variables in SPSS, basically using dummy coding. So I appreciate you watching, and you guys have a great day.